Okay, so we're going to start with a little recap from last week, which is going to be related to the Bohr model of an atom. So if we remember back to the Bohr model, the key thing with the Bohr model was that this was a model for the hydrogen atom. As we'll talk about in a few minutes, it doesn't work for many other things besides the hydrogen atom. But the main thing is that this was the first picture to include quantum ideas. So what this means was this was the first picture of an atom where this was the first picture of the atom where energy was quantized, and what this meant was the sort of the picture that Bohr came up with was this idea that we have a positive nucleus, and then we have these orbits around the positive nucleus where the electron is in, and as the electron gets further and further out. So this was n is equal to 1, 2, 3, 4. So as the electron gets further and further away, the energy goes increasingly up. So if this is n is equal to 1, this is n is equal to 2, 3, 4, 5, for example, 3, 4, and 5. So as we get further and further away from the nucleus, the energy is going to increase more and more. And the idea here was that electrons that are very close to the nucleus, these electrons are going to experience the positive effect. So electrons have a negative charge. The nucleus is positively charged. So these electrons are going to experience a stronger interactive force than electrons that are further away. So these electrons are going to be more stable than electrons that are further from the nucleus, and that's why we get this increase in energy. Now, if you remember, the next guy that we talked about was Rydberg. And he was the one that actually calculated the energies of the electron. So he said that if an electron is in an orbital in the hydrogen atom, its energy is going to be equivalent to the Rydberg constant divided by its quantum number squared, and this is a minus. So this is what Rydberg said, and his constant he had was 2.179 times 10 to the 18th minus 18th joules. So this allowed you to determine what the energy would be of an electron inside of one of these orbits from the Bohr model. And the reason why we cared about this was because we wanted to explain the line spectra. So we know from the line spectra, so if we go back to this slide, the emission from an element comes in these discrete single wavelengths. It's not a broad spectrum, but just these single wavelengths. So he had to explain this idea in terms of transitions from the orbitals of an atom. So he said that one of these lines, one of these emission lines, could be explained, for example, in helium, by the transition of an electron from n is equal to 4 to n is equal to 1. So these have different energies. So the energy difference has got to be the energy of the photon that's given off. So what he said was that the energy of the photon has got to be equivalent to the energy of the initial minus the final level. So we're going from a high level to a low level, so we're going to give off energy, and that energy is going to be in the form of a photon. What he suggested was that if this is the case, we can start to plug in the terms for each of these energy levels, and then we can also plug in the energy of a photon. So we know that the energy of a photon is equivalent to Planck's constant times the frequency. That's from, this is V. And he said that this has got to be equivalent to the difference. So this is going to be the difference between RH of n initial squared minus RH of n final squared. And there's going to be a negative here. Okay, so if we do some rearranging, a negative times a negative, this is going to cancel out and become a positive. So we can kind of rearrange this guy to be a positive RH over NF squared minus RH over Ni squared. And we can pull out the RH, so we can get H nu is equal to RH 1 over NF squared minus 1 over Ni squared. And then if we divide both sides by h, we get the frequency is equivalent to RH over h times 1 over nf squared minus 1 over ni squared. So this equation tells you what the frequency of light will be from a transition in an electron from any one of the two states that are there. Now, I showed you the derivation, but you can also derive, knowing that C is equal to lambda nu, you can also plug in for this, and we can get a second equation. So I'm going to flip over here. Starting with the frequency is equal to RH over h. So this is what we have from the previous page. 1 over nf squared minus 1 over ni squared. And we know that C is equal to lambda times the frequency. So what's going to happen here is if we get frequency, we can say that that is equal to C over lambda. So we can just rearrange this guy and then plug that in. So C over lambda is going to equal RH over h, 1 over nf squared minus 1 over ni squared. And then we can bring the C down to get 1 over lambda is equal to RH over hc, 1 over nf squared minus 1 over ni squared. So this gives us two equations, one in terms of the frequency and one in terms of the wavelength, that allows us to calculate what the output of a photon will be from any one of these transitions inside of the atom. And we went over a problem in class, so I'm going to show you this guy where we did this. So this problem, just to kind of recap, it asks you for the wavelength of light in nanometers. And then we can calculate that for a transition from n is equal to 3 to n is equal to 1. So I'm going to use the 1 over lambda equation, where this is RH over nc times 1 over nf squared minus 1 over ni squared. And so we can plug in the Rydberg constant, which is 2.179 times 10 to the minus 18th joules divided by, this is an H, divided by 6.626 times 10 to the minus 34 joules seconds. That's Planck's constant, times the speed of light, which is 3.00 times 10 to the 8th meters per second. I will give you all these constants on the exam, so you don't have to worry about that. So that's one thing that you don't have to worry about. And then we can deal with our 1 over nf and 1 over ni. So in this case, our final is going to be 1, because it's going from 3 to 1. So that's going to be 1 over 1 squared minus 1 over 3 squared. Now, just to show you how to handle this with the calculator, the first thing I would do is deal with this guy. So I take 1 over 1 squared. Now, I'm being a little bit pedantic here, but you should be able to see that 1 squared is just going to be 1, but you can plug it into your calculator if you feel like you must. Divided by 1 over 3 squared minus 1 over 3 squared. So you get this value, then we're going to multiply it by all of this jazz. So 2.179 e to the minus 18th, and then we're going to divide by 6.626 times 10 to the minus 34, and then we're going to divide by 3 second e to the 8th, and then we get this. Now remember, this is not the answer. This is equivalent to 1 over the wavelength, so we have to do a quick inverse, and then we get our wavelength, which is lambda equals 1.026 times 10 to the minus 7th meters. And then keep in mind that this guy asks for the answer in nanometers, so we do our final conversion, which is for every 1 meter, there's 1 times 10 to the 9th nanometers. So I can do this in my head, and I know that this is going to be 102.6 nanometers because minus 7 and 9, so it's going to shift it by 2. So that's your final answer. Now, actually, with this guy, the sig figs are not really all that important because all of these constants have a large number of sig figs. So you just got to give your answer to a reasonable number of significant figures. So, for example, since I'm asking for nanometers, I would have taken 102. I would have taken 103 nanometers or 102.6. That's just sort of the endemic to this type of problem where it's all constants. So this is how you handle the Rydberg part. Now we're going to move on to things that we discuss that we're going to be discussing in our class, in our upcoming class. So this is going to be the stuff that's new. So we're going to move on now. Okay, so moving on, the next part of this chapter goes into basically proving the Bohr model wrong. In a sense, the reason why we don't use the Bohr model anymore is because it was incorrect. It did not explain everything. So to kind of give you a sense for what was good and bad about the Bohr model, we can kind of talk about that. So we can talk about what was the importance of the Bohr model, and also what was the limitations of the Bohr model. This is very important to understand. Basically, this tells you what was going on at the time and what could the Bohr model do and what could the Bohr model not do. So why was it important? So our first item of importance is that this is the first quantum picture. Okay, so this is the first time. This is the first time that the idea of quantum, meaning that energy comes in discrete energy levels, was used to describe the behavior of an atom, and this is the first time that they were able to explain. This is the first time they were able to explain the line spectra that they were observing. To an extent, and basically what I mean by this is they were able to calculate. They were able to calculate the energies, so they could calculate the energy of the photons that were emitted. But the problem with this was that it didn't explain everything. So when we talk about the limitations, this could not, so the Bohr model, it could not account for the fine structure of the line spectrum. So what do I mean by this? So if you look at the line spectra, even though these lines are relatively sharp and pretty clear cut, if you look at them very carefully, there are actually little spikes inside. There are these little sort of drops and peaks even within one of these lines. It's a little hard to see in this image, in this printer copy, but there was a lot of sort of variation even in one of these little lines. The other thing they couldn't explain was why this line was so weak, whereas these lines were much more were much stronger. So what it came down to was, this idea that yes, we can get the energies right, but no, we can't calculate all these other things related to the line spectra. The other thing that it could not account for was it could not, the Bohr model could not account for the behavior, so it could not explain the spectra for more complex atoms. So the Bohr model only works with one electron systems. So for example, H is a one electron system. A hydrogen atom has only one electron. Helium plus, that's a one electron system. Lithium 2 plus, and so on and so forth. So the Bohr model only works with these systems, but it does not work with everything else. So these were all problems with the Bohr model that at the time limited its use in terms of being able to solve problems of the day. So what we're going to talk about now is we're going to now move toward, so in the next portion of this chapter, we're going to move toward quantum mechanics. And we're going to kind of build up through time through a couple of different scientists of the day toward this idea of quantum mechanics, which can explain all of these things. So we're going to start with de Broglie and then work our way all the way to Schrodinger, who was the one that sort of got the full picture. He got the correct answer. So the next person on our list is called de Broglie. And de Broglie, he sort of, his theory was a little bit odd. He said, and if you want to think about it, he said that light interacts with matter. We know this. If you look at the color of your shirt that you're wearing right now, light, which is a wave, comes and interacts with your shirt, which is matter, and then that's how we get something like color. The only way we can get color is if we have light. In the absence of light, we don't see color. So his whole theory was this idea that there's got to be this duality, because in order for waves of light to interact with matter, that must mean that matter has got to be somewhat like a wave, and light, which is a wave, has got to be somewhat like matter or particles. So that's what de Broglie's theory said. So his theory was that if light, which they knew at the time, if light rays behave as both waves and particles, so he knew that if light waves act as both waves and particles, then he said that particles must also have wave-like properties. So what this meant was that waves must have some particle-like property in order for them to interact with particles, which must also have some wave-like property. And this is going to make more sense in a few minutes as we continue on in the chapter. But the important thing to understand is that there's this idea of a duality. And by duality, I mean that there is a wave-particle duality. So even though it's strange to think about, we as human beings, which are large macroscopic things, not only we have mostly particle-like properties, but we also exist in some small fraction as a wave. And this is the only way that light can interact with us. So what he basically said was that the wavelength of a particle has got to equal h over mv, where this is the mass of the particle times the velocity of the particle. So in his equation, he said that, okay, he used some relatively smart ways of coming up with this, but the conclusion was that every particle has a wavelength, and that wavelength will depend on its mass and its velocity. So the key thing to understand is that as mass goes up, the wavelength of a particle must go down. And this makes sense, right? Because we don't think of ourselves in our world. We don't think of a ball. When we throw a ball to a pitcher, we don't think of that ball as being a wave, because the mass is so large that its wavelength is almost insignificant. The only time this really becomes significant is when the mass is very, very small. And the time that mass becomes very, very small is when we start to deal with electrons. So let's take, for example, so here's an example of how this wave-particle duality kind of works. So I could ask you on the exam to calculate the wavelength, I'm going to use a symbol for wavelength, in picometers of an electron traveling at 2.19 times 10 to the 6th meters per second. So here we go. So here's an electron. This is a subatomic particle, very, very, very small mass, traveling at a speed, and they want to calculate the wavelength. So keep in mind, an electron is definitely a particle. It's not a wave, but it does exhibit some wave-like properties, and we can actually calculate what the wave-like properties, where this electron's wave-like properties will be, what type of light this would look like. So if we come back to our equation, lambda is equal to h over mv, we can start to plug some things in. So we get 6.626 times 10 to the minus, I got to remember here, minus 34 joules seconds, divided by the mass. So you don't have to memorize the mass of an electron. This will be provided for you on the exam. Times 10 to the minus 31 kilograms. So again, this is a tiny, tiny, tiny mass. This is a very, very, very small mass. Much smaller than any one of us by many, many orders of magnitude. Times 2.19 times 10 to the 6th meters per second. So we're just plugging this in. So the frequency that I calculate from this is 6.62, let's clear that out. 6.626 times 10 to the minus 34 divided by 9.11 times 10 to the minus 31 divided by 2.19 times 10 to the 6th. There must have been a mistake there somewhere. I made a mistake. See, I put a division sign. See, I could tell you already that this is not going to be the wavelength of an electron, so I know that. So, see, that's how I can tell if I make a calculator error, is by looking at the number and saying, no, that doesn't look right. So we do e to the minus 31 times 2.19 e to the minus 6th. Now, remember, I have the parentheses here so that I make sure that everything on the bottom stays on the bottom. Now we get a number that looks better. We get 3.32 times 10 to the minus 10th meters. So this gives us a wavelength in meters, and then we have to do our final conversion, which is to convert this to picometers. So I know that for every 1 picometer, there's 1 times 10. For every 1 meter, there's 1 times 10 to the 12 picometers. So this is going to equal this guy times 1 e to the 12th. So this gives me 332 picometers. Now, again, in this case, we do have some sig figs. So the sig figs are going to be 3, since they gave us a speed here. So we're going to report our final number in 3 significant figures. Okay, so this takes care of de Broglie. Now we're going to move on to the Heisenberg uncertainty principle. Heisenberg was the next guy to come along, and if you thought de Broglie was kind of weird, Heisenberg is even a little bit weirder. Quantum mechanics gets a little weird in terms of some of the conclusions that you get out of it. And it's mainly because we're dealing with tiny, tiny objects moving at very large velocities. So this is not something that we can experience on our size scale. We deal with macroscopic objects moving at relatively slow velocities. There's nothing in our world that moves close to the speed of light, whereas an electron can move very close to the speed of light. So what Heisenberg said was that, what we should do is we should start with the Bohr model. So what the Bohr model said was that, Bohr said that you can get an equation, and you can solve this equation for both the position and the velocity of an electron. But as time went on, they proved that this was actually impossible. They started to do careful experiments, and they found out that you actually cannot accurately measure both the position and the velocity at the same time. So this comes down to what Heisenberg did and his uncertainty principle. So the Heisenberg uncertainty principle says, the Heisenberg uncertainty principle says that you cannot calculate an electron's position and momentum at the same time. I should say exact. What this meant was, if you calculate one, so let's say that we calculate the momentum, which is just another way. The momentum is kind of another way of saying velocity. but it's a little different. It's sort of the energy of one way of looking at the energy of moment. So if you calculate the momentum very accurately, you lose information and accuracy in the position. So this becomes very important because this tells us that we can only calculate certain things about the electron before we lose accuracy on something else. This has a lot of philosophical sort of considerations, but when it comes to Schrodinger, who we're going to talk about next, this sort of lays the foundation for the key challenges that come along with quantum mechanics. Now, one thing that I want to stress is that this applies only to very small objects. And by small, I mean objects with very small mass. So when we're talking about these things, we're not talking about a baseball. This obviously does not apply to something like a baseball, which has a relatively large mass. If, for example, the uncertainty principle applied to a baseball, we would not be able to hit it because we wouldn't know where it was and how fast it was moving. We need to know both of those pieces of information to hit a baseball. So the only time this applies is to very small objects moving at very high velocities. And when you get to larger and larger objects, like de Broglie said, the wave-like property of that object goes away. So then all of a sudden, the Heisenberg uncertainty principle, the uncertainty in both of those two variables starts to go away. So with very large objects, if we combine de Broglie and Heisenberg, de Broglie says that the quantum effects go away, whereas when you go to very small objects like an electron, de Broglie says the quantum effects apply. So Heisenberg uncertainty principle, which is a quantum effect, only applies to very small objects. So after Heisenberg did his work, Schrodinger, who was the next person, Schrodinger is the one that really is the one that figures all this out. Schrodinger combines, this guy was in the 1920s, Schrodinger combines the Heisenberg uncertainty principle with the de Broglie principle, and he is the one that really comes up with the picture that we use today. He comes up with this picture called quantum mechanics. And quantum mechanics are what define our picture of atoms and molecules and everything today. And fundamentally what Schrodinger did was he calculated wave equations. So he did this for electrons. So all of his equations were related to electrons. So he treated electrons like both a particle and a wave. He includes the particle. He includes the wave nature. Hence the wave equation of an electron. And he also includes the particle nature. So he includes the particle nature because he uses these wave equations to solve for things like he solves for the potential and kinetic energy of an electron. Okay? So the potential and the kinetic energy, these guys are terms that we apply to macroscopic objects. Kinetic energy is like a ball moving. Potential energy is also like a ball moving, is also related to a ball moving. So he combines for the first time both particle and wave nature into one picture that really does describe the nature of the atom. So the solutions to the wave equation is a wave function. So the next major thing was the solutions to his wave equations are wave functions, and this sounds kind of complicated, but really I think what you'll see is, in essence, what a wave function becomes is just an orbital. And we're going to talk about orbitals in a second, but I think you guys remember back to your days in high school maybe, where we talked about an s orbital and a p orbital. So when he solved these wave equations, what he basically came up with was the shapes of these orbitals. So what I mean, though, just to give you kind of a sense, is so these orbitals, they describe the energy and the allowed energy states of an electron. So just like the Bohr model did, Schrodinger also says, okay, here's an equation that will tell you the energy of an electron, and his calculations, his descriptions, these match or they agree with those of the Bohr model. But an advantage, though, was that he was able to, for the first time, his calculations were able to explain the fine structure in emission spectra. And what you're going to see is that this is due to the fact that the shells are not composed of only one. The shells are not composed of only one type of orbital. The shells, meaning one orbit, like as in Bohr. What the Schrodinger picture kind of shows you is that the shells are in fact made up of many different orbits around the nucleus, and these are the so-called orbitals. So the solutions are the orbitals we know today. So he describes these things as orbitals, and I think when you see the pictures of the orbitals, you're going to recognize them. So an orbital is a region of space where an electron is most likely to be found. Now, this brings in this idea of why is it most likely? Why is it not definitely where an electron is going to be? Why can't we say that this is absolutely 100% going to be where the electron is? And we have to think back to the uncertainty principle. So the uncertainty principle it basically says we can't know the momentum and position at the same time. So what we get is the orbitals are basically these regions where we can find an electron, but because we know the momentum of this electron very accurately, that comes out of the wave equations, because we can calculate the potential energy. So we know the kinetic energy accurately. So we can't know the position very accurately. So what this means is that we can only really, the best that we can do is calculate a rough estimate for where the electron is going to be inside. And we can say that it's going to be most probably inside of this region of space. Now let me show you what I'm talking about. So when we talk about orbitals, these pictures should start to look very familiar to you. Here we have the s orbital. So these were all the different orbitals that came out of Schrodinger's equations. And we can see that there are s orbitals, there are p orbitals. So the s orbital is basically just a sphere. The p orbitals, these guys are as if you were to take two different balloons and put them together. and kind of attach them at the center point, you get these two different lobes. That's what a p orbital looks like. Then the different p orbitals are oriented along the different axes. So we have one going kind of into and out of the paper, one going up and down, and then one going along this y-axis. So in this case, we have the d orbitals, and these guys look like you put 4 balloons together and kind of held them at the center. So you get something that looks like this. We also get this interesting shape here, which looks like 2 balloons held together. And then we get this ring of electron density around the middle. So that's the dz squared. But all of these different shapes, what these are the calculated. So if an electron is in a p orbital, this shape defines where the electron could be found. So it's not saying that the electron is definitely here or definitely there or definitely here, but it says that most likely it's somewhere in this region. And this is the outcome of Schrodinger combining the uncertainty principle combined with the uncertainty principle. So this is really what Schrodinger did. So Schrodinger was the one that sort of defined all of these different orbital shapes. Now what we're going to do next is we're going to talk about quantum numbers. So the way to think about quantum numbers is this is like an address for an electron. So when we talk about quantum numbers, we're going to assign each electron a set of numbers that allow you to determine its exact energy and position in terms of what orbital it's in the atom. So the quantum numbers are really an address, quote unquote, for different orbitals and for the electrons that are in them. Now, if you think about an address, right? So an address is a pretty complicated thing. It has, starting from the back, we can say it has this. It tells you first the state, where the letter has got to go. So that's sort of the last thing that appears. Then the next to last thing that appears is the town. So that tells you what part of the state it has to go to. Then it tells you what street. So we're kind of narrowing it down. And then finally what the street number is. So quantum numbers are exactly like that. It tells you for an electron where exactly that electron is going to be inside of the atom, down all the way from what shell is it in, all the way into what spin state is it in. So you're going to see that now. So the first quantum number that we have to be concerned with is what we call the principal quantum number. And this is sort of like saying what the state is of an electron. So just like we have the United States, so if the United States is the entire atom, the first thing we have to specify is, okay, this is a big atom, so we need to specify exactly what state this electron is in. And the letter we give this is N, just like the ones in the Bohr model. Now, it turns out that when we talk about state, in the other one, we're talking about geographic location. But in this case, when we talk about the principal quantum number, this, in terms of the H atom, it defines the energy level. Okay? So we're not talking about where it is geographically, we're talking about where it is in terms of energy. And again, this is going to relate to the Bohr model. So the N here is almost the same as the one that's in the Bohr model. It basically says that if you're in this N quantum state, then you're going to have a certain energy. And N can vary from 1 through any positive integer value. So 1, 2, 3, 4, 5, 6, 7, 8 to infinity. As we know from the Bohr model, the same thing applies. So as you go up in N, the energy increases. So as N goes up, the energy increases. And for the same reasons, because much like the Bohr model, as we increase N, we're changing the interaction of that electron with the nucleus. And this is where those interactions are going to come into play. Now, the thing that's important to understand is that N, orbitals within a given N within a given value, within a given value of n, belong to what we call the same shell. So it's very much like the state analogy. States are broken up into many, many, many towns, but all of those towns are part of the same state. So what we're saying is that any orbital inside of an n value, all of the orbitals that make up that n value, they're all part of the same shell. So rather than using the term state, we use the term shell. So that's the analogy to the address. Okay, so the next quantum number we have to be concerned with is the angular momentum quantum number. And this gets the symbol script L. Now, what this tells us is, okay, so now the first thing we do is we specify the energy of the electrons. So in a hydrogen atom, if we say n is equal to 1, all of the electrons inside of that n is equal to 1 are going to be the same energy. That's only for the hydrogen atom, though. We'll speak about that a little bit more detail in the next chapter. But we have to say, okay, well, what orbitals are they in? So are they in an s-type orbital? Are they in a p-type orbital? So this defines the shape of the orbital. And what we see is that, again, as the value of L changes, we're going to get different types of shapes. Now, in a hydrogen atom, I want to note this. In a hydrogen atom, all L's, so all of the different L quantum numbers within an n quantum number have the same energy. But in atoms with multiple electrons, we're going to talk more about multiple electrons. So multiple electron atoms, this is actually not true. There are slight variations in the energy as a function of L. Now, don't worry about this too much right this minute, but I want to just sort of introduce and discuss that point. So now let's talk about for L. So we have the angular momentum quantum number. Let's talk about what values we can have. So for n, we can have some different values. So for L, we can also have different values. So it turns out that L, the possible values are going to be as follows. They're going to go from n minus 1 through 0. Okay, so what does this mean? So let's say that we have n is equal to 1. Well, the possible values of L are going to be the following. L is going to equal n minus 1 to 0. So in this case, if n is equal to 1, then n1 minus 1 is going to be 0. So the only possible value of L at n is equal to 0 is 0. Now, if we come over here, if we come over here, we can see that probably this L is equal to 0 is going to correspond to one of these shapes, and I'm going to get to that in just a second. But if we keep going, so n is equal to 2, we can then go over here and we can say, okay, well, 2 minus 1 is going to be 1, so we're definitely going to get L is equal to 1, and then we have to go to 0, so we're going to get 1 and 0. So it's any integer value between n minus 1 and 0. So for n is equal to 3, we're going to get L is equal to n minus 1, so that's going to be 2. We have to get 1 because that's an integer value between 2 and 0, and then 0. And so on and so forth. So for n is equal to 4, we would get L is equal to 3, 2, 1, and 0. Now, what does this mean, though? So what do these numbers mean? Well, it turns out that we can, these numbers actually correspond to different shapes. So the L orbital, so L is equal to 0, turns out that this is an s orbital. So when the L quantum number is equal to 0, you have an s orbital. When L is equal to 1, you have a p orbital. When L is equal to 2, you have a d orbital. And when L is equal to 3, you have an f orbital. So that's what this tells you. What this tells you is, so these quantum numbers, these are the possible numbers you can have for each n, and then each one of these tell you what type of orbital you can have. So for L is equal to 0, so if we want to plot out the possible orbitals, the possible orbital here would be an s orbital. The possible orbitals here would be an s and a p orbital. The possible orbitals here would be an s, a p, and a d orbital. And then here it would be an s, a p, a d, and an f orbital. So if we come back over here and we take a look at this guy, what we can do is we can start to assign quantum numbers to these shapes. So when L is equal to 0, we get a spherical shape, and you can only have one spherical shape because it's centrosymmetric about all of the axes. So when L is equal to 0, we get only one s orbital, and there can only be one of those. Now, when L is equal to 2, when n is equal to 2, we get two possible L numbers, 1 and 0. So these guys are either going to have an s orbital and a p-type orbital, and then so on and so forth. So when L is equal to 3, we can either get an s orbital, a p orbital, or a d orbital, and so on and so forth. So this tells you so when L is equal to 1, we get a p orbital. When L is equal to 2, we get a d orbital. And then when L is equal to 3, we have the electron in a f orbital. Okay, but if you look, you can see, though, that in some cases there are more than one type of p orbital. So how do I know if an electron is in this p orbital or in this p orbital? Well, L doesn't give me enough information to figure that out. I need more information than just L. So the other quantum number that we're going to use to do this is the magnetic quantum number. So the next quantum number on our list is the magnetic quantum number. And the magnetic quantum number has the symbol m sub L. And what this tells you is this defines the orientation of the orbital in space. Okay? So this is going to tell us which type of p orbital it is. So here's the range. So the possible range is as follows. It goes from minus L through 0 to plus L. Okay? So what does this mean? Okay, so let's make a little chart here where we have L and then we have m sub L, and we'll go through. So if L is equal to 0, well, if we go from minus 0 through 0 to plus 0, the only possible m sub L has got to be 0, right? You can't have a minus 0 and a plus 0, so you can only have 0. So what about when L is equal to 1? Well, in this case, we're going to go from minus 1 to 0 to plus 1. Now this sort of is starting to make sense, right? Because let's pull back our picture here. So already we're starting to see some trends. So L is equal to 0. Well, we only get one m sub L. So there's only one orbital that comes out of this equation. So in this case, our m sub L, the only value of m sub L we get is 0, and this is our one s orbital, our single s orbital. Now, it makes sense that when we have three different types of p orbitals, for L is equal to 1, we get three different m sub L's. We get a minus 1, a 0, and a plus 1. So we're assigning now each one of these orbitals, with a different m sub l value. So this m sub l value tells us if it's in this one, or this one. Now let's go ahead and do for 2. So for 2, we're going to get minus 2. We have to work in integers towards 0, so we're going to get minus 1, plus 1, and then plus 2. Right? So whenever you're doing this, it's minus l, and then every integer between that and 0. So it's going to be minus 1, 0, plus 1, plus 2. And then for 3, we get minus 3, minus 2, minus 1, 0, plus 1, plus 2, and then plus 3. So now let's look here at our d and l equals 2. So when we have l equals 2, we have 1, 2, 3, 4, 5 orbitals. So this is going to be m sub l equals minus 2, minus 1, 0, plus 1, and then plus 2. So each one of these orbitals gets a different address, and those are the different m sub l values we get. And again, here we get m sub l value. We get m sub l values minus 3, minus 2, minus 1, 0, plus 1, plus 2, and plus 3. So these m sub l values tell you where you are in each one of these different classes of orbitals. Okay. So the last one that we have to deal with is the spin quantum number. Now the spin quantum number this is related to the fact that we can have 2 electrons in any one orbital. So one orbital can contain up to 2 electrons. Okay? And the way that this works is we know from, and we're going to get into this in more detail in the next one, no 2 electrons can have the same quantum numbers. That's impossible. So if 2 electrons can be in one orbital, so let's say we have n is equal to 2, l is equal to 1, and then we have m sub l is equal to, so this can be either minus 1, 1, or minus 1, 0, or plus 1. So let's just pick plus 1. There can be 2 electrons inside of here. So what we do is we assign a spin quantum number which defines these 2 electrons inside of that one. So in this given one, the spin quantum number defines the orientation of the spin axis. Of an electron. And there are only 2 possible combinations. So the possible m sub s value. So I'm sorry, I should have said the symbol for this is m sub s. So the only 2 possible m sub s values are positive 1/2 and negative 1/2. So in reality, what's happening with the spin quantum number is when you put 2 electrons that are in one orbital. So 2 electrons in one orbital, the spin of the electrons have got to be opposite each other, because this is one way that they can interact with each other. They basically form a magnetic field when they're spinning, and the magnetic field, it's kind of like the poles of a magnet. They have to line up. So you have to have a plus side with a minus side. And that's what this is. So inside of this one orbital, you can either get a plus 1/2 and a minus 1/2. And this describes, this is a minus. And this describes the 2 possible addresses for the electron. So we know that this electron has an energy that's related to the second shell. This is going to be in an L is equal to 1. So we know from our previous thing that this is going to be in a p orbital. It turns out that it's in the p orbital that's defined by the positive 1. And one of the electrons is going to have a positive 1/2 spin, and the other electron is going to have a minus 1/2 spin. So if you want to go through and kind of do this all the way out, we can create a table where we do n, l, so these are all possibilities, m sub l, m sub s, and then the number of electrons, we can figure this out. So when n is equal to 1, we know that L can only be L is equal to L minus 1 to 0. That's the rule. So in this case, the only possibility is L is equal to minus 1, so the only possibility here is that this is a 0. We know that M sub L ranges from minus L to 0 to plus L. So the only possibility here is a 0, minus 0, plus 0, so 0. M sub S, the only two possibilities for the electrons in this is going to be a positive 1/2 and a minus 1/2. So one electron is going to get the address 1, 0, 0, plus 1/2. The other electron would get the address 1, 0, 0, minus 1/2. So how many electrons can we get? Well, the maximum number of electrons we can get is 2 in the first shell. Okay? So this is the first subshell. So in the second subshell, we have two possible quantum numbers. Okay? So we get L is minus 1, so that's going to be a 1. And then again, we get 0 because we go from L minus 1 to 0. So we get a 1 and a 0. So again, in subshell 2, quantum number L is equal to 0. The only possibility here is a 0. So again, we get our plus 1/2 electron, and we get our minus 1/2 electron. So these guys are going to be 2. And then here, we get 3 possibilities. We get minus 1, 0, and plus 1. And each one of these guys is going to have 2 possible electron positions, plus 1/2 and minus 1/2. So this gives us a grand total of 6 electrons inside of this. So the grand total number of electrons in this subshell is going to be 8. So that's the maximum number. And then for n is equal to 3, we have 3 possible L's. We have a 0, 1, and then L minus 1 is going to be 2. So I'm going to give that a little room because we're going to have a number. So again, in 3, if we're in n is equal to 3, L is equal to 0, the only possible M sub L we get is 0. And again, we get a plus 1/2 and a minus 1/2 address. So your electron can either be at, think of this as kind of like the apartment. It's either apartment A or apartment B. They can't live in the same apartment. So again, this is going to contribute 2 electrons, this particular orbital. So this is one orbital. R1 is going to give us 3 different orbitals, minus 1, 0, and plus 1. And each one of these, again, are going to bring 2 electrons, each one with their own address, with their own apartment address. So it's going to give us 6 electrons. So these are our s orbitals, these are our p orbitals, and now we have our d orbitals. So we can go from minus 2 all the way through to plus 2. So these are our 5 different d orbitals, and each one is going to get 2 possible electron addresses. So we can get as many as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in total, this guy is going to give us a grand total of 18 electrons in... Oh, I'm sorry. You guys couldn't see that there. So we had minus 2 to plus 2. And then in each one, we have a plus 1/2 and a minus 1/2. And this is going to give us a grand total of 10 electrons. So to kind of show you guys, so this is going to be an s orbital. And our s orbital can have 2 electrons. This is our, as we build up, this is our s orbital, which has 2 electrons, and these are our p orbitals. So in the first subshell, we can only get s orbitals. In the second subshell, we can only get s and p orbitals. And then in the third, we get s orbitals, p orbitals, and then d orbitals. Okay? So let's look at one possible type of question that we can get from this. So the most common type of question that we get is this idea of, well, tell me, based on your knowledge of these things, if the quantum numbers are allowed. So here's what I want you guys to do. Take a second, pause the video, go through and look at these quantum numbers, and tell me if these quantum numbers are possible. So I want you guys to do this on your own. Think about this. and tell me if the quantum numbers are possible. Meaning, tell me if you can get if these quantum numbers can actually work. So pause the video, go through and do that, and then we'll come back and we'll talk about it. So presumably you've paused the video and you went through and you tried them. So let's go through and take a look. So the first one, n is equal to 0, L is equal to 1, m sub L is equal to 0, and m sub S is equal to positive a half. Now before we even get started, the rules for n, I can tell you already this is a problem. This does not work. Because we know that n is going to be 1, 2, 3, so on and so forth. There is no such thing as an n is equal to 0. When we wrote down what the possible n values were, it was either 1 or over in terms of integer values. So this is not a valid address. So you'd get a return to sender on that one. Now let's look at the second one. So n is equal to 2. Well, that's okay. But we have L is equal to 3. There's something wrong here, because remember, L can only range from It can only range from n minus 1 to 0. So in this case, if n is equal to 2, our possible quantum numbers would be 1 and 0 for L. So this guy automatically makes this address not valid, because the only possible quantum numbers with n is equal to 2 is L is equal to 1 and L is equal to 0. Those are the only possible quantum numbers. Now let's look at the next one. So n is equal to 3. Well, this is okay, because we have an integer value greater than 3. So let's look at the possible L's. So L is going to equal n minus 1 through 0. So in this case, we should be able to get 2, 1, and 0. So this one's okay. Now let's look at m sub L. We know that m sub L ranges from minus L through 0 to plus L. So in this case, we should be able to get minus 2, minus 1, 0, plus 1, and plus 2. And we see already that this is a problem. This is not valid, because this is not anywhere between minus 2 and plus 2. We can't get plus 3. So for the last one, let's take a look. So n is equal to 3, that one's okay. We proved here that L is equal to 2, that's okay. M sub L is equal to plus 2, well, that's okay too. M sub S. This is no good. We know that m sub S can only equal a positive 1/2 and a negative 1/2. So this is not valid. So this pretty much concludes everything there is to know about Chapter 7. So the only thing I want to stress is when you go back, you should look at the beginning part of this. You should look at the beginning part of this chapter, because it has a lot of useful information. So keep in mind that so the important things with this chapter is you have to know how to work with waves and photons. So you have to know how to use Einstein's relation, and you have to know how to use Planck's relation, where you go energy is related to either the frequency or the wavelength, substituting from, in this case, from C is equal to lambda nu. Then we talked about the Bohr model, so you should know about that, and you should also know about the two different equations that are relevant to this, which we showed today. You need to know about quantum mechanics, so de Broglie and his equation. Notice that for Heisenberg uncertainty principle, there are no equations that you have to memorize, but you should know the main points from section 7.4. And for your help, to help you guys, I summarize everything there is to know about quantum numbers. The only thing I want to point out, though, is that in the original version, this is wrong. N does not equal 0. I will correct that. But if you have one, you can cross that out right now. That was just a little boo-boo when I was typing it up. So this describes everything that you need to know about the quantum numbers and what's possible and what's not possible. Okay? So that's it for Chapter 7. We are going to continue a little bit into Chapter 8 today, so that we can get a head start for next class. If anybody does wind up having any questions about Chapter 7, you can always email me those questions and we can talk about them.